Oh, okay. So can everyone see the canvas on my screen? Yes, okay.
Yeah.
All right, so this is your homepage when you sign into Canvas, where most of the stuff is going to be is in the modules. Okay, and I think you're already kind of used to that, but I did change some of the layouts. I just want to talk through that. Okay, so if I click on modules, all right, there's a new box at the top that I wanted us to take a look at. So this will is the logistics module, and what it has in there, it has a direct link to the Zoom room along with the password. The password will stay the same every time. A few of you have already found that there's an updated summer schedule link. All right, so if you click on that, then it takes you to what I hope will be our schedule for the rest of the summer. Okay. This is something that is a live document, meaning it's linked to my Google Docs, so I can make changes on here and it'll be reflected on here. But if we take a look at this week, we have 5.2, 5.3, basically all of chapter 5. And then on Monday, you all will have your first exam with me. Okay. Now, if you weren't able to make yesterday's very last minute Zoom meeting, the exam is not going to be on my math lab, but it's going to be on Canvas. So you'll be able, it'll feel very much like an in-class test in the sense that I'll like have it, the document there, and then you can either print it out or just write your answers to the questions on a separate piece of paper. That's totally fine. No judgment on whether you have access to technology or you don't, just whatever works best for you to have that information be translated. Okay. So if you scroll through here, you can look at this on your own time, but it has the rest of the exam dates laid out for the rest of the semester. I did have to make some adjustments to the pacing to make sure. I think the number one thing I wanted to make sure we got to is the things that will be useful again in Calc 2. Okay, so a lot of this stuff in pre-calc actually comes up again in Calc 2. So I'm really trying to focus this second half of class on things that you may see again, not necessarily in Calc 1, but in Calc 2. All right. A lot of the stuff that's going to come up in Calc 1 is stuff that you've already learned about. And then the second half is mostly things that are applicable for Calc 2. Okay. So that's where you can find that updated schedule. If you go back to the logistics, there is a tab on how to take and submit classwork and exams. I'm actually going to have you read this on your own time. We'll go over this tomorrow in case anybody has any questions, but I don't want to spend too much time today on announcements because we do have a lot to cover, okay? Okay. So chapter 5, I moved it right up to the top. So whatever the newest chapter that we're working on should be the one all the way at the top. Okay, so after chapter 5 is done, then I'm going to move chapter 6 up there and so on and so forth. Okay, I streamlined the tabs a little bit more, so I just want to show you what you have. So for example, today we're covering 5.2. So if you click on 5.2, it'll bring you to a page that looks something like this. Okay. If you click on the 5.2 blank notes, it will bring you to the blank notes that you can either print out or import to your tablet and then write directly on there. And when we're done with class, I will upload my version where it says 5.2 complete notes. Okay, so in case there was something you missed, you'll have the blank version as well as the complete version. When we're done with class today, I'm going to upload the video to YouTube, and the link will be right here where it says Zoom class, June 23rd, 20. Okay, so everything you need for every section will be built right into that section, so you don't have to click between a whole bunch of other things. The last thing I want to point out is that your old professor had left some extra resources, videos for you. So I included those in the link as well. So, but they correspond to whatever section. Okay, so I didn't get rid of them. All the videos are still there. But if it's a video that deals with 5.2, then it's in the 5.2 section. If it's a video that deals with 5.3, then it's in the 5.3 section. Okay. And all of the pages that you're going to have for each section and each day that we do will be modeled like this. So you'll see the blank notes, you'll have the complete notes at the end of class, and the video link for Zoom and potentially other extra resource videos on here as well. Okay. All right. Are there any questions about this setup in Canvas so far? All right, so the other thing I wanted to point out is that for this week, the classwork is going to be optional. All right, so we're just going to give both you folks as well as myself some time to adjust. This is an optional assignment, and it will be worth up to 5 points of extra credit on the exam that you have on Monday. Okay. I also know that your professor had lecture notes for everything. So her lecture notes are in this tab. They are not the same as the ones that I have, but they do cover the same content. Okay, so if you're looking for her lecture notes, you'll find them here. But I'll be posting my own notes, so you'll have more than one resource to help you out. Okay. All right, let's go back to the home page. I think the only other thing I maybe want to point out to you is I'll be sending out announcements. So I think your old professor sent out emails. I'm going to be sending out announcements via Canvas. And so you'll be able to find all the announcements here. And I like to send out one announcement a week. So I usually send one out like Friday, and that'll tell you about all the stuff for the upcoming week. All right, so all of those will be pushed out via announcement. And then grades, you know where to find your grades. And yeah, I think that's it in terms of the changes made to Canvas, okay? So if anybody has any questions, please let me know. I'll hang around at the end of class and I'm happy to answer any questions that you have about Canvas or the class moving forward, okay? All right. So we're going to go ahead and get started. And we're going to go ahead and start with 5.2. So if you have access to a tablet or a printer, you're welcome to go ahead and print out the blank notes for 5.2. And if not, you can just follow along or print it out later is fine too. All right. So I'm going to go ahead and stop this share, but then I'm going to share my, my tablet screen so that we can walk through those notes together, okay? And if some of this is stuff that you've already learned, bear with me. I think it's kind of hard to step in and not quite know what you already covered and what you didn't cover. So we're just going to start with 5.2 as if you've never seen it before, all right? All right, so today we're going to cover 5.2. All right, so 5.2 in your textbook talks about exponential functions and graphs. All right, so we're going to start by talking about what is an exponential function. And I think that's one of the most important things as you sort of move through through pre-calc is thinking about knowing the different types of functions that come up and what characteristics they have or they don't have. Okay. So one thing that we are probably very used to seeing is something called a power function, okay? So a power function might look something like this. It might be like y equals x. That would be considered a power function. Y equals x squared. That would be considered a power function. Y equals x to the 1/2. That would be considered a power function. So the basis of what makes it a power function is you've got the variable as the base. So like x is a variable, x is a variable, x is a variable. And then you have a constant in the power. So 2, 1/2. And then if we were to go back and say, well, but hey, in this first example, I didn't see a power, that power is actually 1, and 1 is a constant. And that's why y equals x is considered a power function. Okay. Now, what we're going to be focusing on in this chapter is exponential functions. And here's what's different, okay? An exponential function has the constant as the base, and it has the variable in the exponent. So what this looks like is it could look like y equals 2 to the x, right? So we've got our constant in the base, x is our variable in the exponent. So variable and constant. You could also have y equals 3 to the x. That would be considered an exponential function. We're going to see some that look like this. Y equals e to the x. And e is a constant that we'll learn about. And x is our variable. So that's why it's considered an exponential function. Okay. Now, one last thing about exponential functions, you could have a base that is less than 1. That would be okay. And what I mean by that is you could have y equals 1/2 raised to the power of x, and that would be considered an exponential function because you have a variable in the exponent and a constant in the base. All right. So power functions versus exponential functions, good to know what's similar and what's different. Okay. So when we think about exponential functions, sorry about the lag. I'm not quite sure why it's lagging today, and I apologize for that. But exponential functions have a specific form for the equation. So you're going to have f of x equals a to the x, or some textbooks write this as y equals b to the x. All right, so there's different forms, but either way, the a and the b, the thing that is raised to the exponent, that is your determining factor about whether your function is going to be growing over time or if it's going to be decaying over time. Okay. So when we think about exponential functions, I want us to think about these two pictures, all right? So if we have an example where a is greater than 1, and so for example, maybe that's y equals 2 to the x, then we're going to have a graph that looks like this graph, okay? So it starts kind of close to the x-axis, and then it goes up and up and up. And as the x numbers get bigger, the y values get even bigger, really fast, okay? So these tend to grow quite quickly. In contrast, if I have a graph of something that is like y equals 1/2 to the x, okay? We're going to have a situation where the function actually starts with a very large y value and then gets closer and closer and closer to the x-axis, all right? And so we consider that a case of exponential decay. Things are losing value, okay? So when we're thinking exponential functions, we're thinking a curve, not a line. And we're thinking growth means we're going up in value and decay means we are going down in value. And we can tell from our equation based off of our a value, all right? So bigger than 1 is growth, between 0 and 1 is decay. Okay. So that was a little foundational piece about what an exponential function is. And so now what we're going to do is we're actually going to jump right into equation solving. And I know that these are in the last section of your textbook in chapter 5, but I wanted us to kind of get a head start about like what it is that we're doing with these exponentials and how we might start to build a toolkit of strategies that we can use to solve. Okay. All right. So let's take a look at example number 1, okay? So I've got 2 to the x minus 1 equals 2 to the 2x minus 4. Now, what is one thing that you folks notice about this equation?
They have the same base.
They have the same base, exactly, yeah. What color did I use for the base? I forgot. Pink, okay. So in this case, they have the same base. So I have a 2 here, and I have a 2 here, okay? So let's for a moment imagine that I asked you this question instead. 2 to the x equals 2 to the 5. What does x equal?
X equals 5.
Yeah, how'd you guys know that so quickly?
Well, as far as I know, if they have the same base, so the equation is equal to each other.
Perfect.
Yeah.
Very nice summary. So if the bases are the same, that means that our exponents, or the things in the yellow, have to be equal to each other. So in this very simple case, x equals 5. And what we have here is just a step up where we have x minus 1 has to equal 2x minus 4. Perfect. Thanks, Michael. Yep, same base. So you set the exponential functions equal to each other. Good. So now we can simplify this equation just to say x minus 1 equals 2x minus 4. All right. And so we have a linear equation here, and we're just going to combine our like terms. So I'm going to move all of the x's to one side, and I'm going to move all of just the constants to the other side. So I'm going to take this x and I'm going to subtract it from the left-hand side, but also from the right-hand side. And then at the same time, I'm going to take this 4 and I'm going to add it to this side and to this side. Okay. So -1 plus 4 is going to give me 3. And then 2x minus x gives me 1x. And so in this case, we've got x equals 3. Okay. And let's just kind of plug that back in to check and make sure that that's correct. So 2 to the 3 minus 1 equals 2 to the 2 times 3 minus 4. This gives me 2 squared. And this side also gives me 2 to the 6 minus 4, which is 2 squared. All right. So what we have here is we have a single solution of x equals 3. And we did check our answer to make sure that when we plug it back in, it still works. Okay. Now, when we were younger and maybe like elementary, middle school, high school, it was really important for us to check our answers because sometimes we made calculation mistakes. And as we've kind of grown in our math, we now need to check answers not only to make sure we're correct, but to make sure that the answer we got is actually an answer, okay? So that's going to be a really important theme in this chapter is, are the answers actually answers, or are they something called an extraneous solution? All right. So that's something that we want to keep an eye out for as we move through this chapter. Is the answer really an answer, or is it extraneous? So if we plug it back in like we did in example number 1 and it works, we're good to go. But if we plug it back into the equation and it doesn't work, then that is considered an extraneous solution. Okay. All right. Let's take a look at example number 2 over here. All right. So example number 2 is a little bit different, right? Because I have a 3 for this base and I have a 9 for the other base. 3 and 9. So one thing that I cannot do is I don't want to say 5x minus 8 equals x plus 2, all right? So let's actually go ahead and say it's not equal to that because we don't want to fall into that trap. But sometimes we can make it look like a situation in example number 1 where the bases are the same, okay? So what's another way for me to write 9?
3 times 3.
3 times 3, great. Rephrase that in a way where I'm using exponents.
Second.
So I've got 3 to the 5x minus 8 equals, instead of 9, we're going to write what you just said, 3 squared x plus 2. Okay? So it's starting to look like example number 1. Now we're going to do a little bit of algebra here. When I have a power raised to another power, I multiply those two powers. So on the right-hand side, I really have 3 to the 2x plus 4, because I have to take the 2, multiply the x, and take the 2 and multiply to the 2, okay? Now, look what we've created. Base is 3, base is 3. So 5x minus 8 can equal 2x plus 4. Okay? So once we get the bases the same, then we can set the exponents equal to each other. So I'm going to do the same thing I did on the last side. I'm going to move all my x's to one side and all of my constants to the other, and let's see what we get. So I'm going to subtract 2x, and I'm going to add 8. And I get 3x equals 12, or x equals 4. And now let's plug that back in just to double check our answer. 3 to the 20 minus 8 equals 9 to the 4 plus 2. So 3 to the 12 equals 9 to the 6. And you have a few options. If you wanted to double check this on a calculator, you could certainly do that. But let's use how we were able to rewrite 9 as 3 squared to help us see that they're the same. So 3 to the 12 equals 3 squared to the 6. And again, when we have a power raised to a power, we multiply them. All right, so we've got x equals 4. We plug it back into the original, works out. So x equals 4 is a solution to our equation. All right. Any questions about example 2 or 1? Okay. Let's move on to example number 3. Okay. So sometimes it requires a little bit more front-end work to make the bases look the same. All right. So I've identified a base on the left-hand side. I've got a base of 1/3. So life would be pretty nice if I could come up with a base of 1/3 on the other side as well. And so what I'm going to do is I'm going to go ahead and divide both sides by 36. Okay. And when I do that, I end up with 1/3 to the x over 5. Don't be scared by the fractions. It's okay. Equals 4 over 36. And if we think back to elementary school or middle school and we're trying to reduce our fraction here, 4 goes into 36 9 times. So 4 over 36 is actually the same as 1 over 9. Okay. Now that's super nice because check this out. We can do 1 over 3 to the x over 5 equals 1 over 3 to the power of 2. And now we've created that situation where we have a base and they're equal. So that means x over 5 can equal 2. So x over 5 equals 2. How do we get rid of that 5?
Multiply reciprocal.
Yeah, we're just going to go ahead and multiply by that reciprocal. And so we'll get x equals 10. Okay. And now let's go ahead and plug that back in and make sure that we get the right answer. So 36 times 1/3 to the 10 over 5 equals 4, hopefully. This is 36 to the 1/3 squared. Do I multiply the 1/3 by 36 first, or do I square it first?
You square it first.
Yeah, we square it first. Now, I know we didn't get to 141 and not know our order of operations, but sometimes in the middle of a harder problem, it can just be something that we forget. So we kind of want to make that an active choice that we are squaring or raising something to a power first before we multiply. So 36 times 1 over 9 equals 4. And that's really 36 over 9 equals 4. And 4 equals 4. So I know that my answer of x equals 10 is a solution. Okay? So I just wanted to start with a couple sort of straightforward problems where the goal is either it's already has the same base, or with a little bit of algebra, we can make them the same base and therefore answer the question. Okay? Now, the next part that we're going to talk about is graphs and graph transformations, all right? So one of the things that is really helpful if you are a math major or you even have to take calculus, like if you have to take calculus, knowing the shapes of your graphs and knowing graph transformations, like how you can tell from an equation what the graph looks like, is actually a really helpful skill, okay? So let's take a closer look at the exponential function graph. So again, we have f of x equals a to the x, and some textbooks write this as y equals b to the x, okay? So it's just important that you have a constant to a variable. The actual letter doesn't really matter that much. But here are a few key features for this graph. You have something called a restricted range, okay? If you look at this graph, there are no negative y values. And so that's what this 0 to infinity means. It means that we only have positive y values that come out of the basic exponential function. Now there's a second feature on the graph that is a little hard to tell sometimes. So let's just make sure we highlight this. And that is that there is a horizontal asymptote at y equals 0. So this horizontal asymptote is at y equals 0. And so I think you've seen asymptotes when you talked about rational functions, but basically what this means in this case is our graph gets super close to the x-axis, but it never actually crosses it, okay? It doesn't actually ever have a y value of 0. The last feature that I want us to be aware of here is that there is a y-intercept at 0, 1. And so that's this point right here, okay? So when we think about an exponential graph, those are sort of the main features we're looking for when we graph them. Did we get the range right? Did we get the horizontal asymptote? And what's that y-intercept? Okay. Okay. So as I mentioned before, there are some really important ways to think about how graphs move and how you can tell from the equation, all right? So let's say you have an exponential function, and at the very end, you add some number. Okay. So if you're adding a positive number, what that does is it moves your graph up. Whereas if you subtract that number, you're actually going to move your graph down. Okay. This will change the horizontal asymptote, because when we move things up and down, we're going to see a change in the asymptote. Okay. One thing I do want to sort of maybe make a connection for is what does that graph look like?
Parabola.
Yeah, this is a parabola. Okay, so I know that this is a parabola. What do you think that +3 does?
Shifts it 3 units up the y-axis.
Exactly, exactly. Same shape, right? But it just moves it up 3. And so these graph transformations, like that number at the end, if we add it, is always going to move our graph up or down. It doesn't matter whether we're looking at a quadratic or a cubic or a rational function or a polynomial or an exponential function. Anytime we have that plus whatever at the end, that's going to shift a function up or down. On the flip side, if I have a number that I'm adding or subtracting to the x value, that is going to shift my graph to the left or to the right. And things that are a horizontal transformation are always the opposite of what you think. And what I mean by that is that a plus c, you would think plus means like positive and it means to the right. Nope. It actually moves our function to the left. Okay. And similarly, if I see a minus number there, it's going to move my function to the right. Now, because I'm moving left and right, this does not change my horizontal asymptote. All right. And so an example of this might be if I had my y equals x squared, but instead of x squared plus 3, I did x plus 3, and then I squared it. Which direction does that move my parabola?
To the left.
Yeah, this is going to take that parabola and move it to the left. And if we think about what that might look like for an exponential function, maybe we have y equals 2 to the x plus 3. See how that plus 3 is in the exponent? That's like that plus c. That's going to also take my exponential function and move it to the left 3. Okay? So it doesn't really matter what kind of function. These graph transformations are pretty universal. All right, so we've got vertical and horizontal shifts. And then the other one that's kind of important for exponential functions is reflection, right? So once again, we have 2 different types of reflection. We have a situation where we have a minus sign in front of the whole thing. And then, if you maybe anticipated, we've got a minus sign that's only with the x, only in the exponent. Okay, so the location of that minus sign matters. If you have a negative sign in front of the entire thing, just like with polynomials, it's going to reflect over the x-axis. Okay, so that's not different than the other functions we know. What that means is if I have a regular exponential function, okay, so let's say I have an exponential curve and it goes like this, and I reflect it over the x-axis, then it's going to look something kind of like this. Okay, so this second graph is what it might look like if you have a negative a to the x. Now, if that exponent is the one with a negative sign, then that's actually going to reflect it over the y-axis. Okay, so not the x-axis, but the y-axis. Now, both reflections, they don't change the horizontal asymptote. So the only thing that's going to change that horizontal asymptote is if you shift it vertically, moving things up and down. Otherwise, that horizontal asymptote stays at y equals 0. And here's a picture of what a reflection over the y-axis would look like. And so instead of starting low and ending up with a large y value, we're going to start with a large y value, and we have something like this. Okay, so you might even think about this one as like growth and decay are kind of like reflections over the y-axis. One goes up and then the other one goes down. All right, so let's take a look at 3 examples right here, and let's think about the graph transformation. So we're going to describe the transformations. We don't need to worry about graphing them, but I want us to be able to identify and predict what's going to happen to that graph. Okay. Now, I purposely use the letter E here because that's something that you see a lot in Calc 1 and also in Calc 2. All right, but E is a number. So E equals a constant. And we'll talk more about that at the end. All right, but E is a constant. All right, so take a moment, look at example 1 and example 2, and see if you can write down what transformations are happening. And then we'll share out some answers in about a minute or so. All right. Can anyone tell me, for example number 1, what that 100 does to the graph?
Shift it down.
The 100?
To the right. I mean,
Wait, to the right, yeah.
Yeah, that 100 is in the exponent, so we know it's a horizontal, and the horizontal is always the opposite of what you think. So it's not left 100, it's going to be a right of 100. And you can just write it like this, to the right 100. That's fine. Or you can use words, really whatever works better for you. Okay? Now, what about this 200 at the end, this plus 200? What does that do?
Shift it up.
Exactly, it's going to shift it up 200 units, okay? Now, part of why I want us to be able to identify the graph transformations is I know in this day and age, you have Desmos, you have graphing calculators, you can graph them and see what the graph looks like, but sometimes it's useful to think about like what's happening to the graph. It'll make some of those calculations when you get to Calc 1 and Calc 2 just a little bit easier, okay? All right, what about example 2? Someone else tell me what's happening in example 2.
Reflected across the x-axis.
Yeah, this minus sign is a reflection over the x-axis. Good. All right, what else is happening?
Down 5 units.
Perfect. -5 at the end means we go down 5 units. Okay. Does the horizontal asymptote change in example 1?
Yes.
Yeah. What does it change to? It was at y = 0.
200.
Yeah, it does. So we can say that our horizontal asymptote, okay, I like to abbreviate because sometimes it just takes me a long time to write. So HA stands for horizontal asymptote, and we can write that as y = 200. Okay. And how about for example 2? What is the horizontal asymptote for example number 2?
-5.
Yeah, y = -5. Okay. Now, I really want us to make sure that we're writing like the y equals, because when we get to the log graphs or the second half of the chapter, we're going to need to change the y to a different letter. Okay, so here we have our horizontal asymptotes at y = 200 and y = -5. All right, let's take a look at one last example here. Okay, so example number 3, we have f of x equals e to the 2 minus x. So what do we think is happening with this?
Going to the
Reflecting over y-axis.
I agree with that. Any ideas about that too?
Left 2.
Are you saying left 2 because it's a +2?
Yeah.
Okay, all right. I agree that there's a plus sign there, okay? But this example, I wanted us to do an example like this because this is maybe like the #1 way to write like a trickier graph transformation question, because we actually have to do a little bit of algebra before we can determine the graph transformations, okay? So I agree with the plus, but let's do a little bit of algebra. So what I mean by that is I could write this as e to the -x plus 2, right? -2 or +2 minus x is the same as -x plus 2. Here's the tricky thing about the reflections in the power. You actually have to factor out that minus sign so that you can tell whether the graph goes right or left, okay? So that's something I really want us to be on the lookout for. If I factor out this minus, it turns it into x, not +2 anymore, -2, okay? So we're right in the sense that this has a reflection over the y-axis, but we would be incorrect if we said it moves to the
Left.
left, okay? So this -2 means that we're gonna have it move to the right 2, right? So when we see the reflections over the y-axis, I want you to make sure to factor out the negative sign, okay? So make sure to factor out the negative sign so that you can get the proper horizontal transformation, all right? What is the horizontal asymptote for this particular graph?
0.
Yeah, and we want to be specific and say y = 0, okay? All right, So we've taken a look at two cases that are maybe a little bit more straightforward, right? We're just picking the numbers. Where are they? How does that impact a graph? And then this is definitely worth knowing that when we have a reflection over the y-axis, we need to make sure that we factor out that negative sign so that we can get the correct horizontal shift, okay? Any questions about the graph so far? All right. So we're actually going to finish off this section with applications of exponential functions. And I think your textbook also saves this for the end of the chapter. And I understand why. I think it seems like maybe it's more difficult, but I actually, if you don't like word problems, because like the wording can be kind of tricky right now, exponential functions are actually what I think to be the most straightforward word problems that there are in all of math, okay? They're very formulaic, and we're gonna be looking for a few things, but setting up the equation for our exponential functions from a word problem is actually pretty easy, okay? So before we go and look at some applications, what I want to do is write out the formula for exponential function and talk about what each of those letters represents in a word problem, okay? Now, there are actually so many applications for exponential functions. That's the other reason I really like it. As someone who's maybe thinking about studying some sort of biology, we often use exponential models to look at population growth or bacteria growth. If you're thinking about going into finance, or you simply want to know more about like, what do interest rates mean? Like if I want to take out a loan, how much do I actually have to pay back? Or if I put my money into a savings account, like how much am I actually going to earn? We use exponential functions to talk about all of that stuff. So it's actually very applicable to the work that we are in our everyday lives. And that's kind of cool, I think, at least. All right, so here is the exponential equation that we want to use when we're looking at word problems. So we're gonna have y equals b times a to the x. Now, sometimes that dot, the multiplication symbol, is not there, so it might look like this, b a to the x. Now, it's less important like what the letters are called and more important where the letters are, okay? So if I have the number that is raised to the power, so a, okay? A is the one raised to the power. In every word problem, you're either going to have or be asked to find the initial value or starting value. That's what your A is. So A in a word problem is your initial value, or sometimes it's called a starting value. And I am so sorry, I don't mean A, I mean B. Okay, so whatever is the number in front, that is your initial value or your starting value. So let's say that you wanted to buy a car and you wanted to buy a car that was $10,000. $10,000 is your initial value. Or let's say that you wanted to open up a savings account and you wanted to put in $100 into your savings account. To start, that's your B, or your starting value. Or let's say that you are counting the population of squirrels in your neighborhood, and on the first day you count that there are 25 squirrels, then 25 would be your initial value or your starting value. The A, or the number raised to the power, what that represents is the growth or decay constant. Okay, the growth or decay constant. So if A is greater than 1, it's going to be a growth curve. That means the next day you would have more money in your savings account, or the next day there would be more squirrels in your neighborhood, okay? But if it is a number between 0 and 1, then we're looking at a decay scenario. So if you buy that new car, the next day it's going to be worth less money. It's a decay situation. Or you walk around your neighborhood and you realize there are fewer squirrels than there were the day before. That population is decaying or going down in value, okay? Now, all the questions that we're gonna see are gonna have percentages in them, okay? And I will give you a formula for how to find A, but I want us to write right here that A is not equal to the percent given in the word problem. Okay, A is not the percentage given in the word problem, but I will give you a pretty easy way to find A. All right, we got a couple other letters left. Whoops. X. That number in the exponent. All right, this number in the exponent is going to refer to time cycles. Okay, so if we are looking at the percent of change every month, then X will be in months. If we're looking at a rate of change every year, then X is going to be in years. Okay, so it's usually the amount of time that passes. The final letter that we have is this Y. And the Y is not your initial value or starting value, but it's actually your ending value. Or some folks call it a desired value, like the value that you're going for. Okay? So in every single word problem that we see with exponential functions, we're going to start off by writing y equals ba to the x. Every single one. And then we'll fill in what numbers we have, and then we'll see and try and solve for what they're asking for. Okay? So the big takeaway from applications is we want to start with y equals ba to the x. That's what we're going to start with. All right, so let's try one of these applications. All right, so there's that equation again, in case that you want to write your stuff down there. But let's start with this scenario, okay? So some folks are the kind of folks who are like, look, if I can, I want to buy a new car. And by new car, I mean like brand new car. You know, no one else has ever driven it before, and I'm going to be the first person. It's got that new car smell, and it's just going to be wonderful, okay? And some people are more in the camp where it's like, I don't want to pay for a new car, or I can't afford a new car. It's not worth it to me. That's not where I want to put my money. And so they might choose to buy a used car. Okay. The thing with most cars, and by most, I mean like there are exceptions, like very classic cars might have not adhere to this rule, but most every car, the moment you drive it, every time you drive it, it loses value. So you buy a car. Let's say, in this case, my friend Erin was actually looking at purchasing a Toyota Tacoma. She's like, I want a small pickup truck, and so this is what I want to get. And the average cost of a brand new Toyota Tacoma is $36,000. Now, this particular model depreciates by 17% each year. Okay, I would say that cars depreciate anywhere between like 15 to 25% every year. So this word depreciate means that it is losing value by 17% every single year. Okay. So there's two parts to this question. I would like us to write a function that models the value of the car. And then I want to find out how much Erin's car is going to be worth after 7 years. Okay. So we're going to start off by saying I see a starting value and I see a percent. And those two indicators tell me I better write y equals ba to the x. Okay. What number can I fill in for b? And how do you know that?
36,000
How do you know that?
because it's the first price.
It's the initial price, exactly. She wants the brand new car. That's how much she's going to have to pony up, 36K. All right. So let's see, what colors did I use? Green, purple, orange. Okay. So we have a B value, or an initial value, of 36K. Our A value, all right, this is where I said it's not 17. It's not the percent in the problem. And here's the formula for how you find your A value. Okay, so to find A, we're going to say that A equals, we're going to draw a fraction line, and we're going to have 100 plus or minus the percent in the word problem. And after we do plus or minus, we're going to divide it by 100. Okay. Now, one quick thing here. This plus or minus is not like plus or minus in quadratic formula, where you do one and then you do the other. This plus or minus is a choice. Okay. So if the value is increasing, like the amount of money in your savings account or the number of squirrels in your neighborhood, if that percent is increasing, you're going to add that percent. But if that number is going down in value, like this new car, we need to do subtract. Okay. So what we're going to do for A is we're going to do 100. We're going to subtract 17 because this car or this truck is losing value. We don't even need to do 0.17. We literally just take the percent right out of the word problem and put it right there. Okay, so you do not need to change it into a decimal. Then this divided by 100, that's the part that turns it into a decimal for you. Okay. And we're going to leave this as an X right now. The reason I'm going to leave it as an X is because the first part of the question says write a function that models the value of the car. So I just want to write this function, and I'll simplify the A value, excuse me, to be a number. So this is going to simplify to Y equals 36,000 times 100 minus 17 is going to be 83. And then 83 divided by 100 is 0.83 raised to the x power. So this is my answer to the first part, which is write a function that models the value of the car. Now, let's start plugging in values for x, okay? So this question says, find the value of Aaron's truck after 7 years. This is in years, and this is in years, so I can just take 7, plug it in for x. So after 7 years, we would get y equals to 36,000.83 to the 7. Okay. Now, I asked this question earlier, but I'm going to ask it again. Do I take the 0.83 and raise it to the 7th power first? Or do I take the 0.83 and multiply it by the 36,000?
Raise to the 7th power first.
So you're going to raise this to the 7th power, and then you're going to multiply that. If you use a calculator for this, so this section does tend to end up with a lot of decimals, and that's okay. If you type this into your calculator, you could type it in all at once. You can just type in 36,000. And then I would put 0.83 to the power of 7. So depending on your calculator, it might be a little caret symbol. That's how we do to the power. And if you type it in all like this, it'll give you the answer, and you don't need to like write down a decimal and then type in a new decimal. But either way, you should end up with 9768. Now, what are the units for my y? Like, what am I measuring this in?
Dollar value?
So dollar value tells us we want to round to 2 decimal places. So 9, 8. Okay. So to recap, we saw 2 things in this word problem that told us exponential function. The first thing was we had a starting value, and then the second thing was we had the percent. We see those 2 things and we think y equals ba to the x, all right? Now, this number right here, what this tells us is after 7 years, her car is worth less than $10,000. So that's something to think about as if you're ever in the market for a car or a scooter or a motorcycle, okay? Whatever kind of vehicle that you're purchasing for your daily commute, those will lose value. And so how much is it worth for you to buy that new car versus buying a slightly used car, right? That's a very personal decision. But let's do this. Let's see what happens after the first year. Okay, so let's say she paid $36,000. I want to know how much is going to be left after 1 year. So why don't you guys see if you can figure that out? And then let's share some answers and see what we get.
It's gonna be $29,880.
That's what I'm getting too. Okay, so how much money did she lose on that car that first year? About.
6 grand, over a little over 6 grand.
Yeah, a little over 6 grand, right? So that's the difference between saying, hey, I'm just gonna buy the 2019 model, be 6 grand cheaper. Or if you really, really want that new car smell, you have to pay 6 grand more for a car that will, in a year, already have lost $6,000. And so, you know, all of this is to say we all have choice in our, you know, how we spend our money. But especially with cars, this is why some people are like, they like to go to the dealership and buy the 1 or 2 or 3-year-old car because you end up saving a lot of money up front. Okay. That being said, I think my dad bought a used car one time, but he got a really, really rotten deal. He definitely got a lemon, and that car needed so much money in repairs that he didn't end up saving any money at all. And so that's like the downside, right? If you buy from, you know, a not as reputable place or something like that, you might end up in a situation where it needs a lot of repairs. But try and think about what that balance is. Like before you buy a car, how much is that difference? How much do you lose that first year? And is that worth it to you? Okay, so let's take a look at example number 2. Right? So this is more for folks who might be thinking, all right, I'm more like a bio major or even public health or any sort of situation where you're looking at populations, okay? So this can be for animals, it could be for humans, it could be for bacteria. But this one, we're gonna take a look at manatees, all right? There's some pretty cute videos of like baby manatees out there if you haven't seen them. They're just kind of like round and floppy. But they used to be on the endangered species list. Pretty sad. So let's say that there are currently 13,000 manatees in the entire world, and that the population is growing by 1.5% each year. I would like us to figure out how many manatees will there be in 5 years, okay? So I'm gonna give you a minute to set up your equation, and then I'm gonna share my equation up here, and then we'll compare, and we'll make sure that we get to the right answer, okay? So go ahead and set up that equation, and I'll give you a little bit of a head start. Okay, so hopefully we wrote down immediately y equals ba to the x, and not just because we're doing a lesson on exponentials and this is the equation I gave you at the beginning, but also because we saw a starting amount and we saw a percent, okay? So 13,000 should be our b, or our starting value, and then we know that we don't want to put 1.5 in for our a, but that we can use that handy dandy little equation where we have to choose whether we do a plus or minus. And so my question to you here is, do we add or do we subtract that 1.5? And how do you know?
Adding,
Adding, how do you know that?
because it's growing by 1.5 each year.
Perfect. It is growing by 1.5 because there are more and more manatees. So we want to add that 1.5, okay? And so when we do 100 plus 1.5 and we divide it by 100, we'll get 1.015. And I think it's a syntax preference whether you choose to have the x on the outside Or it is acceptable to write this with like the 1.5015 to the x on the inside. Those two say the same thing, but the second one will probably get you a number on the calculator a little bit faster, okay? Now in this case, instead of x, we want to plug in 5 because it's 5 years. So that will give us y equals 13,000, 1.015 to the 5th power. And again, if you have a calculator, you could just type that all in at one time. And we should get about 14,004.69205, okay? So one of the common questions I get from students is like, we're looking at all these decimals, like how many decimal places should we round to? And I would say the answer to that depends on what you're measuring. So if we think about example 1, we were talking about money, so we rounded to 2 decimal places. But in this case, we're talking about animals, and so really we want to round down to the nearest whole animal, okay? I've also had other students be like, well, you have, 14,004 manatees and a pregnant one. That's also fine, okay? So I'm not too picky about the rounding, but I do want you to kind of think about like what you're measuring and what might be appropriate, okay? So money, 2 decimal places, animals, usually round down. All right, so how are we doing so far? Are these word problems okay? So somebody asked a question about whether we round up. And since we're talking about whole animals, if we don't have a whole animal, then we don't count it. So then we have only 4 and not the 5, okay? Michael, what's your question? Are you asking a question out loud? Because I cannot hear you.
Sorry, if you're rounding it to the nearest whole number, is it not meant to be 14005?
Well, we don't have another full animal, though. It's only part of one, so we don't count it.
Okay.
Okay?
Okay.
Yeah. All right, so someone asked a great question. If one unit is in months and the other is in years, how would you go about solving that? I love that question. And we're actually going to see that in the next question, okay? But basically, you want to convert them so that they're in the same time cycle, all right? So if it's at 5 months, we would have to do 5 divided by 12 to get the equivalent number of years, all right? Okay, so on that note, let's move on to example number 3 so that we can see what happens if we need to do a little bit of work to get our x. Okay, so this third question here is another really classic situation when we talk about exponential functions, okay? Now, one thing I think is really important about this question, we're going to read it through once, and then we're going to go back and cross out some of the numbers we don't need, okay? I think some of us a lot of us probably are still at the stage where we're like, I must use every number in the word problem or something is wrong. And this is actually a really great example of sometimes they give you more information than you need, and it's not applicable to your particular question, all right? So Hg 197, or mercury 197, is used in kidney scans, and it has a half-life of 64.128 hours. Write the exponential decay function for a 12 milligram sample, then find the amount remaining after 72 hours. Okay? So I'm going to go ahead and cross out one number. In fact, I'm going to cross out one whole thing. Okay. The reason why I'm getting rid of that is because I don't need that 197 in my equation. That 197, right, maybe let's cross it out so you could still read it. That 197 is talking about the type of HG that's used, it doesn't have an impact on how much we start with or how much we end up with. Okay, it's like the name of the thing used in the kidney scan. So we don't need that 197 there. And with a lot of these questions where it says a half-life, you're often going to have a number that you don't need in there. So if it's part of the name of the thing, cross it out. Don't worry about that number. Okay. So I see a few things. I see half-life, and I see a starting amount. Now, half-life is code for you lose 50% every half-life cycle. Okay. So a half-life is, let's think about this. So I actually slept funny the other night, which is why I have this like heat wrap on my neck, because I feel like an old lady and I can't turn my neck real well right now. And so this morning I was like, I should probably take some Advil to help with the inflammation in the area. Now, if you've ever read an Advil or a Tylenol or any kind of medicine, it usually says like, take this every 4 to 6 hours or take this every 12 hours. And where they get those numbers from is from the half-life, okay? So a half-life means if you start with a certain amount, after one half-life, you have half of that amount left. And after another half-life, you have only half of that left. And so if you keep counting half-lives, after a certain point, the medicine no longer has like an effective level in your bloodstream. So that's why they ask you to take another dose to kind of get that level back up again, okay? And so the half-life for Tylenol and Advil and things like that, turns out that they've measured like how long it takes to go down in value, and then it's between 4 to 6 hours depending on like how old you are, how much you weigh, what your tolerance is to medication. So there's like a lot of factors. That's why they give you a range of 4 to 6 hours, okay? So right here, we have a half-life of this thing in the scan, all right? So let's actually start with a little chart. I start with 12 milligrams. How many milligrams do I have after one half-life?
6.
Yeah, it drops down to 6. And then how much do I have after another half-life?
3.
And then after that one?
1.5.
Okay. And then it kind of keeps going, right? So every half-life, I lose half the amount. Well, the question we have to ask ourselves is, how long is the half-life? So for example, a half-life for Tylenol and Advil, it's not 4 to 6 hours, but it's shorter than if you've ever taken, I think it's Aleve, is like you only take it once every 12 hours. Or some of the heavier meds, you only take it once every 24 hours. That's because those half-lives are longer. It stays in your system longer. And so you don't have to take the medicine as often, okay? So with this half-life, in this particular case, the half-life is 64.128 hours. That means that after 64.128 hours, you have 6 milligrams left. After another 64.128 hours, or a total of like 128 hours, You have 3 milligrams left at about 128 hours. Okay. How many hours have passed since this first went into your bloodstream that you would have 1.5 milligrams left?
256.
It's actually not 256. So we don't keep doubling the time. We have to keep adding the half-life. So we're going to add another 64 to this, and that'll bring us up to about 192-ish hours. Okay, so we keep adding on a half-life, or we multiply it by the number of half-lives that we have. Okay, so looking at our little chart, can someone estimate for me about how much we're going to have after 72 hours?
7-ish? 7-ish?
You say 7-ish,
Or 5-ish?
5-ish? How'd you get that?
Because 64 was is the half-life, so it went into the 72 hours a few times and it had a little that bleeds over.
Perfect. Okay. I love the way that you phrase that, because that is exactly how we're going to figure out for sure how much is left after 72 hours. Okay. So let's go back to an equation. Y equals BA to the X. I want to know how much is left. So I want to find the Y. My B, or my starting value, is 12, because that's how many milligrams I start with. My A is going to be 100 minus 50 over 100. And here's what's going to be different. In my exponent, whatever my time is, I actually have to divide it by the half-life. Okay? So when I divide the amount of time by the amount of the half-life, what I'm going to get is how many half-lives have occurred. Okay? So if we do this next to it, 72 divided by 64.128, we end up with exactly what you said, Michael, which is 1 and a little bit of a half-life. 1.123 of a half-life. Okay? So by dividing it, what that tells us is 1.123 is going to replace the whole exponent. So we really end up with y equals 12 times, this goes to 0.5 to the power of 1.123. Okay. And if we type that into our calculator, then we're going to get about 5.510 milligrams are left. Okay, so you were spot on. You were saying it's going to be a little bit less than 6, so maybe 5-ish. And to be more precise, it is 5.51 milligrams that are left after 72 hours. Okay. Any questions about this half-life one?
So I just have one question. And for so I understand how this all works. It's kind of like a future question. How will we always know how to use that kind of reasoning to solve the problem? The half-life part I understand, but would there ever be any other situations similar to it?
I would say this is like the most classic case one.
Okay.
Okay, great question. Okay. All right, so I think we've got 2 more problems left here, and then we'll be done for today. Normally, I like to take a break, and I sort of blew past that today, so I apologize. But in general, we take like a 5-minute break about halfway through because I know I'm asking you to sit for a very long period of time. Okay, so example number 4. The average rate of return on an IRA is 6% each year. If you invest $6,000 this year in an IRA, find the value of your investment after 30 years. Okay? So we're going to learn a lot of stuff in this class that you may or may not use again, depending on the trajectory of your education, but also in your job. Maybe you need it immediately for school, but after a few years when you're working, you might not ever use this again. Okay? I hope that this is the one thing you remember from this class, all right? So an IRA is called an individual retirement account. And one of the things as an individual in the States is that you can open up your own retirement account, therefore individual retirement account. Now this is separate from if you get a job and your employer pays for part of your retirement. That's different. That's funded by your employer. This is money you put away for yourself for the future. Now, there's actually a limit to how much you can put away for yourself every year. And that limit right now is $6,000. So every year you can only put away $6,000 into, it's basically an investment account, except it's very long term, meaning temporary ups and downs kind of even each other out. And what happens over like a 30-year period is on average, the stock market will increase your investments by 6% each year, okay? That is a very medium risk investment, meaning like we're not taking into account the really, really, severe impact that COVID has had on our economy. And we're hoping that gets balanced out at some point in the future with a very strong year, okay? So on average, we end up with 6%. And let's say that you are so inspired by this conversation that you're like, look, I get my first full-time job. I'm going to take $6,000, which I know is a lot of money. I'm going to take $6,000 in 1 year and I'm going to put it away into my IRA. And then you forget about it. Okay, so let's say you do it 1 year and you forget about it. And then you go to retire and you're like, oh shoot, I have this $6,000 that I put away. I wonder how much it's worth now. Okay, so you haven't done anything other than put $6,000 in and forget about it. So let's write our equation for this, okay? So when we talk about money, there is a fancier version of the y equals ba to the x that we tend to use, okay? So we can use our y equals ba to the x, but we're also going to use this fancier equation, which is a equals p little e to the RT, all right? Now, usually when banks do their calculations or accountants do their equations, they use this form of the equation, but you can get a pretty good estimate with the first one that we use, okay? So let's try using this first one. My initial value is going to be 6,000 because I'm maxing out my IRA for that year. I'm putting in as much as I can for that year. Now, to find my A value, I hope that my money grows in value. So 100 plus 6 divided by 100. And I forgot about it. So my time is 30 years because I forgot about it for 30 years. This gives us 1.06 to the power of 30. So 6,000 times 1.06 to the 30th. And I think we should be getting a number like this. Yeah?
Yeah.
Okay. I know that $6,000 is a luxury to put away. Okay. I recognize that, especially when you're like first starting off with your salaried job and maybe you've just been, doing the poor college student thing for a long time and you're really tired of eating instant noodles all the time. You want to go out, get that avocado toast, your iced coffee, all of this stuff. I know that 6,000 can be a lot. Okay. But the impact of a one-time deposit into this investment account is you gain almost $1,000 every single year. You put in 6 grand, you walk away with almost 35 grand. Okay. This is one of the big reasons why folks say it's important to invest early. So if you are 25 and you start your IRA now, this is how much money you're going to have when you're 55. But if you don't start until you're 55, you're not going to have this money until you're 85, right? So you don't give it as much time to grow if you start later. Now, to be clear with your investment, 6,000 is the max, but even if you put in $100, $500, $1,000, even if you put in something, something is going to grow to more something. Whereas if you put in nothing, it's going to grow to nothing. Okay? Okay. So this other formula. A stands for annuity. Annuity is a fancy word for saying how much money do you have? That's it. P stands for principal, but not like your high school principal. Like principal is a fancy word for the amount you put in, your starting amount. Okay. A lot of times people will say, oh, what's the principal on your account? That's just how much you put in or your current balance. E is a number, right? We've said that E is a number, but it's also a button on your calculator. So if you have your calculator with you, if you could see if you can find the little E button, it's a lowercase e. Usually it's with another button that says LN. Okay. So if you haven't found that button or you don't have your calculator handy, go check that out later because that'll be helpful on like the exams and stuff, okay? But E is kind of like pi where it's a number and it's about 2.718, okay? So let's use this equation and see what happens when we have $6,000 that we have in there for 30 years, okay? So A is 6,000, E. Now when we put in our R, we actually take the percent and we turn it into a decimal. So 6 divided by 100. And then we multiply, and then we multiply that by the time. So RT is the percent times the time. Okay. And when you type that all into your calculator, you end up with 36,297.88. So if you look, I think we would all prefer to have the second side, right? We want to have a little bit more money, even if it's, like $1,500 or $2,000, it's still more money, right? So this formula is actually the formula when we do something called compounded continuously. Okay. So what that means is that every single second, every half a second, you have more money, they pay you the interest on that even more money. So over the course of 30 years, it's almost like $1,500 extra dollars just because they counted faster how much interest you're getting. This one, the first one we did, is smaller because this one, they let your money grow for an entire year, and then they're like, oh, you leveled up, new money for the interest. But they wait a whole year before you get to do that, whereas the right-hand column is something called compounded continuously, which is what pretty much all banks use these days. But it does pay you more interest every single second of every single day, okay? All right, so that's it for today. All right, that's it for today's lesson. I know, again, I apologize that I blew through the break and that we didn't have a chance to do that. But this should hopefully get you started on chapter 5. And tomorrow we're going to take a look at 5.3. It'll be very similar in style. You're welcome to take a look at the blank notes today before tomorrow's lesson. Or if you're unable to make tomorrow's lesson, again, we'll record these Zoom meetings. You'll be able to access them through Canvas on your own time, okay? So if you don't have any questions for me, you're welcome to take off. Have a wonderful rest of your day. Thank you for being so flexible. And if you do have some questions, please stick around and I'm happy to answer those for you, okay?
Teacher, I have a question.
Yes, what's up?
What happened to like?
Do you mind if I stay after class? I have a question to ask you.
Yeah.
Okay, thank you.
Oh,